Before we begin the study of the higher order equations, I think it would be a very good idea to come back up to speed on complex numbers. So I want to do this quick review of complex numbers, and there may be some information in here you haven't seen before. That's going to be pretty important to our work. So first of all, as a basis for a complex number system, we need a unit that we call I. This is called the imaginary unit. And we define it to be the square root of -1. So complex numbers are usually thought of as square roots of negative numbers, or the imaginary parts rather. The imaginary numbers are square roots of negative numbers. And so the triple equal sign, by the way, means by definition. Okay, now the next thing we need is another definition. We need to define what I squared means. And that's a bit of a problem because think about this. What do you get when you square the square root of 3? We get 3, don't we? You could think of it this way and multiply these together, and square root of 9 is 3. That's one way to think of it. Or you could just say, well look, the exponent of 2 is the inverse of the square root, and so they cancel each other, and I can proceed directly to here. Alright, well, we have a problem doing that with -1, square root of -1. Because if I square this and multiply these together, I get the square root of +1, which of course is 1. So why is that an issue? Because if we take the other definition and say, well look, when we have an exponent of 2, it cancels the square root, I should get -1 instead of +1. So that's an issue. And so how do we resolve that? Well, it turns out that defining this as +1 is just doesn't lead to anything useful. And it was deemed, well, we found out that when we define I squared to be -1, then we get a viable number system called a field, the complex number field. And so by definition, we're going to say this is -1, and we're no longer going to allow this. When I multiply the square roots of two negatives, I can't multiply the arguments under the square roots together. No longer allowed. So we just lost something by adopting this complex number system. Alright, so anyway, these form the basis for the complex number system. And if you let A and B be real numbers, then we can define a complex number as A plus B times I. And so the piece of terminology I need you to learn here is that this part is called the real part, and this part here, B times I, is called the imaginary part. Now, it turns out that's pretty important because there are some problems involving sines and cosines where the answer will either be the real part or the imaginary part of something. And so I need you to be able to distinguish that. Finally, just a little digression here. Complex numbers are two-dimensional numbers. They require two pieces of information. And if you were to try to represent this on a number line, you wouldn't have any luck with it. We can't form a complex number line. We can, however, form a complex plane. And the traditional thing is to let the horizontal axis be the real part, or the real axis, and the vertical axis is the imaginary axis, or imaginary part. So for example, if I want to represent 3 plus 2i, it would be right here. Over 3 up 2i, it's a point on the plane, two-dimensional plane. Well, I don't recall if we're going to need this kind of geometry for what we do. But you will need the next thing I show you. And so in calculus, you've learned about, I hope you've learned about the Maclaurin and Taylor series expansions of functions. And one of the first things you do is to work out the Maclaurin series expansion for cosine and sine. I'm going to write them up here. So the cosine of x is expands out this way. It's going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on and so forth. On infinitum ad nauseam. You see the cosine function looks like an infinite degree polynomial. And because it is, it's known as a transcendental function, as is the sine function. But anyway, it's an infinite series, and if you've forgotten what these mean, 6 factorial would mean 6 times 5 times 4 times 3 times 2 times 1, which would be, I think, 120. No, 720. Anyway, you've got a factorial key on your calculator, I'm sure, if you need it. Alright, so there's the cosine, and you'll have to go back to calculus in case you're wondering where that comes from. Look up Maclaurin's series. Now the sine function has a similar expansion. It's the odd version of it. It would be x minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on and so forth. And so you see it's very similar to cosine. Cosine uses even exponents and even factorials, and then sine uses the odd powers. So that's pretty nice patterns here. The other thing I have to point out is that x is expressed in terms of radians here. So x is in radian measures, not degrees. So you can't plug in degrees and expect to get anything here. You would have to convert to radians. Alright, well, I bring this up because another expansion you do in calculus is e to the x. From there, e to the x. And it expands this way. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on and so forth ad infinitum ad nauseam. And it's a very, very wonderful pattern. And you can see right away why the derivative of e to the x is e to the x. You start taking these derivatives and you'll get the same thing back again. So it's kind of neat to see that appear. It would be circular reasoning, though, to argue that because of this, the derivative of e to the x is e to the x, because you have to know derivatives in order to produce that expansion. So anyway, now here's the punchline to all this, that we're going to need Euler's formula in what we do. And Euler's formula. Leonhard Euler was the most prolific mathematician in history. It looks like it's Euler, but it's pronounced Euler. He was German. And he lived from 1707 to, I think, around 1785 maybe. He had a pretty long life. And he published more than anybody in history, and had amazing accomplishments. Well, one of the many things he studied was this natural base number e and this function, and that's why we call it e, in honor of Euler. To my knowledge, that's why we call it e. But Euler's formula is this. It says that e to the I times x is equal to the cosine of x plus I times the sine of x. So it's pretty amazing, but it's not hard to derive if you know these Maclaurin series expansions. If you replace x with I times x in each of these and work it out, you'll see that this formula works. So it's not bad algebra at all to come up with this by using these Maclaurin series expansions. So what's really amazing is that this gives us a way to deal with exponents which have imaginary or complex number exponents. And that's going to come in very handy very quickly here as we get into higher order equations. So it's a pretty amazing way to dive into a new world with exponential numbers with imaginary exponential functions with imaginary exponents. All right, so there you go. We'll need to use this quite a bit here over the next number of videos.